Hi guys, hope everyone's doing well. I figured we would start chapter 10 with a little slide on jelly beans. This follows your notes perfectly, so if you'd like to get your notes out and copy the, as always, green words down, you are more than welcome to. Nevertheless, why do I have a container of jelly beans here? If you've ever been to a carnival or a festival, you always see that they will have a big gigantic container of jelly beans and it'll say, oh, guess how many jelly beans are in there. A lot of people guess under, some people guess way over. Nevertheless, it's always the prize if you guess close as either the jelly bean container or another prize of some sort. Nevertheless, it'd be really nice if we could take that jelly bean container, dump them all out, count them, and guess what? I came up with my number pretty darn easy. However, what if we had something a little bit different? What if we had something a little bit that has a larger number, kind of like sand? Oh, this is pretty. So, if you guys have ever been down to the Regatta in Pittsburgh around the 4th of July, you'll see they always have a really magnificent sand sculpture. This is one of Gollum from Lord of the Rings. But if we were trying to count these individual sand particles, I think that would be almost impossible to do. We would have an infinite number and you'd be sitting there for hours and then the wind would blow and you'd lose count and then start all over and it'd be like a vicious cycle. Horrible. Nevertheless, say we took these grains of sand, which are made up of molecules, and then we took those molecules and actually separated them into individual atoms. This number would be like excruciatingly big and we can't even see something like that. So let me give you a different example. Say gold. Okay, this is pure gold. It's made out of the element, which on the periodic table is Au. What if we wanted to find out how many atoms there are in each one of these pieces of gold? I think it goes without saying we would have to find the mass of each piece, but either way, how are we going to figure out the atoms? So that's where this new definition comes in, and that's called the mole. A mole is simply the amount of a substance that contains 6.02 times 10 to the 23rd, you will be using this number a lot, representative particles of that substance. Alright, this I think raises a bigger question on what the heck is a representative particle. It's a fancy chemistry word that makes us sound super smart. Alright, if you're out on the street and you're talking chemistry as you normally do, you say, oh, it's made up of 6.02 times 10 to the 23rd representative particles. I don't think people are really going to know what a representative particles are. There it is. However, if you were to talk about an atom or a molecule, people will be like, oh, you're not so smart, I know what you mean. But we can use this fancy term called representative particles. So it could be an ion, it could be an atom, it could be a molecule or a formula unit. Here I have atom, copper on the left. In the middle, molecule, H2O. We learned about those with covalent bonding. And lastly, formula unit, kind of a fancy word for a compound like salt. So hopefully you guys watched the video on the mole. I wanted to kind of explore this a little bit more. So let's do a little history lesson. Back a long time ago, in the early 1800s, around 1810, there was this guy named Lorenzo Romano Amadeo. Okay, we're not going to go into all that, but let's just call him Amadeo Avogadro because that was his short name that you will see in chemistry books. So he came up with this thing that he says, okay, if I have equal amounts or equal volumes of gas, they should have the same amount of particles in them. Now, you guys have probably already heard from the last video that there was a such thing called Avogadro's number. And contrary to popular belief, Avogadro did not come up with Avogadro's number. You think he would, because if you came up with something, I'm sure you'd want to attach your name to it, but he had nothing to do with Avogadro's number. Actually, he was dead before the term Avogadro's number was even coined in chemistry. However, there was this guy, and his name was Jean-Baptiste Perrin, and he used Avogadro's research from years ago, and he came up with this Avogadro's number. So what he said was that if we have two containers of gas, they are going to contain the same amount of particles as long as they have the same volume. So then Jean-Baptiste Perrin did more research and finally came up with Avogadro's number being equal to 6.02 times 10 to the 23rd, here's that fancy term again, representative particles. I thought this was cute and funny, so I included it. A little bit of an older song, but I thought it was funny. But before we're done today, guys, I just want to do one thing, and that's kind of introduce you to the mole. So let me explain to you what it means. So on this slide, I have 1, 2, 3, 4, 5, 6 elephants. If I were to compare them to chipmunks, okay, I also have 6 chipmunks here. Obviously, the elephants are going to weigh more than the chipmunks. However, I have the same amount of elephants as I do chipmunks. So, what's the difference between them? This is kind of a good introduction to the mole because the mole is always going to contain 6.02 times 10 to the 23rd particles, or representative particles, as we've been using that term. However, the mass of these representative particles we're using, whether it is compounds, molecules, or atoms, can be different. If you look at your periodic tables, picture that we have hydrogen. Hydrogen, we know, is a diatomic. It's H2. A molecule of hydrogen is going to weigh 2.02 grams per mole, as we calculated in class today. Let me give you a little bit of a heavier atom. Let's do diatomic fluorine, which is going to be F2, as we learned last chapter. It's going to have a molar mass of 38 grams per mole. Now 38 obviously is much, much more than hydrogen. Now let's even relate this back to last chapter, where we started to draw them and we found out that fluorine actually has more energy levels than hydrogen. This means that those atoms are actually going to take up more space. So when you think about it, if we have diatomic fluorine and diatomic hydrogen, that diatomic fluorine is going to be more of the elephants. It's going to be a bigger molecule. It's going to be bulkier. And the hydrogen would be more of our little chipmunks, smaller, not so ginormous in size. However, a mole of both of them is going to always contain 6.02 times 10 to the 23rd representative particles. Okay, we'll discuss this a little bit more today. Hopefully this video helped you out a little bit with first starting to understand the mole. But what I want you guys to do is write down 2 things. 1, something you learned from this video, and 2, either a question you have on the video or something that wasn't too clear to you, so that way in class tomorrow we can kind of take those problems or take those positives and go over them a little bit. Alright, so if you guys have any questions, let me know tomorrow. Have a good night, guys.